Hi there, welcome to a video lesson on growth and decay problems. What we're going to do is just apply some of the things we've been talking about exponential functions and solve some problems involving growth and decay rates. When we look at growth and decay problems, you're going to use this general form of an exponential function. This should look somewhat familiar with the exception of maybe this t over p business, but I'm going to talk about what this means for you. So your y, this is going to be your final amount. And all of these growth decay problems, typically you're dealing with some sort of amount of materials or bacteria. That's going to be your y. That refers to your final amount. Okay, your a is your initial amount, what you're starting with. B is your growth or decay rate. So depending on if you're experiencing exponential growth or decay, that's going to be your b value. T is the time elapsed. P is the growth or decay period. This one can be a little bit confusing sometimes. We're going to talk about that in some of the examples. Just a note here, T and P have to be in the same units. Okay, so if we're talking about minutes or hours or years, these two have to be the same units. So some steps. This goes for all sort of problem solving questions. Always start by identifying what you're given. If you have to write it out in a list, feel free to do that. You're going to see me do that in this video. And then just sort of identify what you need to solve for. You're going to substitute what you're given to this formula, and then you're going to solve for the unknown variable. And you're going to do this using some of the algebra strategies that we've looked at in this unit. All right, so let's look at an example. I'm telling you this is a growth example. Obviously, whoever's giving you this question, whether it be your teacher or somebody on the street, will not tell you that it's a growth example. But if you read the question, it becomes apparent pretty quickly. So it says the number of insects in a colony triples every 2 months. So triple means grows, gets bigger by a factor of 3. And I've kind of color coordinated to the variable in my general expression. So B is going to be 3, or we're growing by a factor of 3. And this takes 2 months. Okay, so 2 months will be my p value, right? P, remember, is the amount of time it takes for the tripling to happen. But it usually follows the growth or decay in your question immediately. So you can see this comes right after the tripling. Okay, there are 1,000 insects in the colony right now. That's your original value. That's your a value. How many insects will there be in 6 months? We've already taken care of the t. 6 months are passing. How many insects will there be? That's going to be the final amount. That's what we're solving for. So we're going to take all this information, we're going to substitute it into this little formula, and you're going to see that you end up with something like this. One thing I want to just draw your attention to, if you are tempted to multiply these two numbers together, do not do that, because that is incorrect. Okay? You can't just simply multiply. BEDMAS tells you that you've got to do your exponents first. Okay, so we're going to do 3 to the power of 3, then we will multiply by 1,000. Okay? Make sure you follow BEDMAS or your teacher will cry all over your test. In 6 months' time, there will be 27,000 insects in this colony. Better call an exterminator. All right, so another example. Working with exponential growth, you've got a bacterial colony that has 262,144 members after 10 hours. How many bacteria were there to begin with if the bacteria doubles every 40 minutes? So if you're like me, I really struggle with problem solving and word problems because I find I'm very overwhelmed by all the information. But it helps to read the problem through once and then sort of go through and underline what you're given, what you need. In this case, the thing that jumps out at me the most is how many bacteria were there to begin with. That tells you that you're looking for the initial amount. So that's going to be your a value. Okay, so you can see I've just identified that I'm going to be solving for a. Looking at the question again, it tells me that I have this many bacteria after 10 hours. So after 10 hours have passed, I've got that many bacteria. So that must be my final amount. The b value, it straight up says I'm doubling. This is the confusing part, is the t and the p. So 10 hours have passed, so that means that it's going to be 10 hours worth of time. Okay, so that's going to be my t value. It takes 40 minutes to double. So remember, p is the time it takes for your growth or your decay. So that's going to be your p value. Notice, if you're keen here, you'll see that I'm working with different units. I've got hours, I've got minutes. Make sure you convert your units. I think in this case, I'm going to stick with minutes. I'm going to say my p value is 40 minutes. My t value, I've got 10 hours. There's 60 minutes per hour. Therefore, I've got 600 minutes. So I'm going to take all this information, I'm going to substitute it into my handy formula, and you can see that unfortunately, I've got stuff on both sides of the equation. I'm going to have to do some algebra here. Okay, I'm going to start by just cleaning up my exponent. I divide those two numbers out nicely. I'm going to raise 2 to the power of 15, and I end up with this atrocious number. I'm not going to bother pronouncing this because I'm trying to make this a nice, concise video for you. we're going to divide both sides by this number here. Okay, I'm not going to write that out just for the sake of time, but we're going to divide both sides by that big number and solve for A. We can conclude that there were 8 bacteria to begin with, and after 10 hours, we ended up with a lot of bacteria, and that's why we wash our hands. Okay, third example here, this one tells you that you're working with decay. Okay, so this is our first decay example. Working with polonium-210, this is a radioactive element. One thing I've seen when I give questions like this on tests is people use this number in their solution. Do not do that. This is just a number that happens to refer to this particular isotope, I believe. What is important is that we're dealing with half-life. Half-life right away tells us that we're going to have a B value of 1/2, and this is going to take 13 weeks. So thinking right away, 13 weeks, that should be your p-value. If there is an initial amount of 24 grams, our initial amount is our A value. How much will remain after 1 year? So our t-value should be 1 year, but if you're keen, you're picking up that our units are not the same. We're dealing with years, we're dealing with weeks. It'd be smart of us to convert into the same unit. So let's take years, write it as weeks. There are 52 weeks in 1 year. Hopefully you know that. If not, now you do. We want to know how much will remain. That's our final amount. We've got everything we need. Let's substitute them into our formula. We're going to do our division in our exponent first. Raise our 1/2 to the power of 4. Remember, you don't want to do 24 times 1/2 first. So you're going to do 1/2 to the power of 4. I just wrote that as a decimal number, and then we'll multiply those two numbers together to get 1.5. We'll have 1.5 grams left after 1 year. Okay, another decay example. So how long will it take for 1600 milligrams of bacteria to reduce to 25 milligrams if it has a half-life of 30 days? I like to chunk things out into smaller pieces. That's why I've underlined these things. How long will it take? That is going to be your t-value. How long does this whole thing take to happen? We've got an initial amount of 1600 milligrams. We want it to decrease to 25 milligrams. That's going to be our final amount. It has a half-life. Half-life will be our B value, and it takes 30 days for the half-life to go by. So that will be our P value. So you can see here we're solving for T. This is going to be an interesting problem because you can see our variable is in the exponent. Well, fortunately enough, we've been working with exponential equations, so we should have no issues solving for that variable. So we're going to substitute everything into our equation. Okay, you can see everything fits in there nicely. We've got an unknown in our exponent. Some of you are thinking, oh my goodness, how am I going to solve for that? We're going to do that using some algebra. So the first thing that, again, you might be tempted to do is to multiply these two numbers together. Remember, you cannot do that. We can't multiply first. We'd have to do our exponent first, and we can't because we have an unknown in our exponent. So let's backtrack a bit. Let's start by thinking, well, you know what? I'm going to make this simpler by getting rid of this 1600, and I do that by dividing. Okay, I can divide both sides by 1600 because this is being multiplied, right? I simply just divide both sides. I'm not going to write that out on both sides just for the sake of time, but those are going to cancel out nicely. So look at that. We've simplified our expression. Some people are thinking, oh my goodness, you now have 2 fractions. I didn't want 1 fraction, let alone 2. So let's think back to solving exponential equations. Well, the first thing we did was applied exponent laws, which we can't really do here. The second thing we did was we took a base and we tried to write it as the other base to some exponent. And that's what we're going to do. We're going to take 1/64, and we want to somehow write this as 1/2 to some exponent. I'm going to take 1/2. Really, all I have to do is find some number I can raise 2 to get 64, right? If I raise 2 to that power and 1 to that power, I should get 1/64. Okay, as it turns out, that number is 6. Okay, 2 to the power of 6 is 64. 1 to the power of 6 is still 1. Okay, so perfect. My bases are the same. Remember, when we're solving exponential equations, we can just drop our bases, solve whatever results in our exponent. Got a nice little linear equation here to solve. So let's multiply both sides by 30, solve for t. So it must take 180 days for 1600 milligrams of this bacteria to decay to 25 milligrams. I'm not sure what's with this example because as far as I'm concerned, bacteria does not decay, it grows. But, sorry about that. Anyways, that should help with growth and decay problems. This one does not make sense, but not all problems do make sense. So I apologize for that.